All right, so for this video, I'm going to dive into sound perception and two major sound concepts that I think are bullshit. And I'm going to play some audio tests that you can listen to, write down the answers, and see if you agree with me or you agree with the status quo. There's been a lot of science and a lot of testing, and they've come up with some stuff which I consider highly dubious. So I don't bias the results. I'm going to start off with some listening tests for you, and you may want to grab a paper and a pen in case you don't remember what your answers are, and you can write those down, and later in this video I will tell you what was going on in those tests, and that should be really interesting. The first test will be pink noise, and there's going to be a reference signal played at a certain volume, and then the volume will increase and it'll go back to reference, increase again, go back to reference, increase a third time, and back to reference. What you're going to be looking for is which of those increases sounds like twice the level of the reference signal. Then I'm going to do the exact same test with a pulse instead of pink noise. All right, so this is important. Your audio hardware may want to really screw with this test. It's going to try and mess you up. And you also may find out that your audio hardware is doing things that you do not want it to do. So you're going to want to turn off auto leveling, because that'll screw up the level tests, and any kind of weird stuff that is in the settings. You want as pure of a playback as possible. If the pulses are intermittent or jumping around in volume in drastic levels, like they were on my laptop, then you want to try something else. I was unable to find a setting to fix that. Using headphones is good, or you may need to switch the listening device to something that's working. And there are no right or wrong answers to this. In fact, all the answers are right. They are just looking at it from different metrics. And what we're trying to do is determine which metric is more correct than the others. Also, you might want to turn things down a bit. Don't have your stuff cranked, because the level will be going up, and don't want to hurt your sound system or your ears. All right, the next listening test will be level perception, and we'll do pink noise and pulses again, and each of those will have 4 different listening sections to it. The first will be the reference, where the pink or pulse will stay the same level. The next 3, the pink or pulse, will be changing in volume or staying the same. And what you want to do is write down whether it's changing in volume or staying the same. And for bonus points, write down how much you think it's changing in volume if it is. And it will be fruit for the pink noise and tools for the pulses. All right, so the two audio concepts that I take issue with is, first, it takes 10 dB for something to be twice as loud. This is kind of a rule of thumb. People perceive sounds that are 10 dB louder as twice as loud and 10 dB quieter as half the volume. But this isn't the case for everything else. For lights, you put 4 lights on it and it's twice as bright. So it's a 4-to-1 ratio for lighting. For kinetic energy, it takes 4 times the amount of fuel or energy to get an object moving twice as fast, according to the formula for kinetic energy. Yet for sound, 4 times the amount of energy would only be 6 dB. For sound, we require 10 dB for it to be twice as loud, which is unlike the other perceptions that we have. Why is it that sound takes more energy for us to perceive it as twice as loud as lighting or motion? This is incongruent. So those audio tests were about figuring which you felt was twice as loud. The other is 3 dB is barely perceptible to most humans. That's the smallest increment of perceptibility in sound level changes that most people can hear. What do you think? Let's take a look at some different perspectives of lines and cubes and square inches. And what I've done is I've converted all of these things into dB, into the logarithmic scale. So we have a common denominator, we have a common reference point. So as you're looking at all the different scenarios, look at how many dB change it is versus what appears to be, in your opinion, twice the amount. Well, all right, so to me, it seems pretty clear that things that are double, twice, the line, the cubes, the square inches, the speed of the cars, were all either 3 dB or 6 dB. Yet sound, we're told, or the tests have shown, that it's 10 dB. So why does it matter whether it's 10 dB or 6 dB is perceived as twice as loud? I mean, these are opinions that people gave in tests. They said, this sounds, in my opinion, to be twice as loud, and it happened to be 10 dB, and the majority of people did that back then. How does that really impact us? Does it even matter? Well, let's say you're putting together a sound system to install in a venue, and you've got a smaller system and a larger, more expensive system. And someone asks you, well, what is better about the larger system? You know, it's louder. How much louder? It's 6 dB louder. Well, how much is 6 dB? Is that twice as loud? Or is it 1.5 times as loud? Or 1 3/4 times as loud? It's 10 dB louder. Is that twice as loud? Or is it 3.16 times as loud? We saw that with kinetic energy. 10 times the amount of energy delivered 3.16 times the speed. If we were to follow that information, if those examples that I gave are correct, 10 dB would be 3.16 times as loud, and 6 dB would be twice as loud. Another example is noise mitigation. You've got sound bleeding into the neighborhood, and you've made a 6 dB reduction. Have you cut the volume in half? Or have you cut it some fraction of that? Do you have to drop the volume 10 dB? And it can work against you as well. If 6 dB is twice as loud and you have 6 dB more noise than ambient, then you're twice as loud as ambient. So it's all about communication. You know, having the wrong data or having 6 dB be twice as loud or 10 dB twice as loud, which do you use and are you communicating well? Are these commonly shared and believed numbers the best way to communicate? All right, so let's talk about the listening tests we did at the beginning of the video. So I played a bunch of pink noise at different levels as well as pulses, and there was a reference followed by a 3 dB increase, which is double the amount of power. If you had a 100 watt amp, you went to a 200 watt amp into the same speaker and it can handle it, you should get approximately a 3 dB increase of maximum output. The next one was a 6 dB increase, which is 4 times the amount of power, going from 100 watts to 400 watts. And finally, the last ones were 10 dB increases, 100 watts to 1,000 watts in order to reproduce that. All right, so now that you know the answers to the audio test, which is it that you perceive as twice as loud? Was it 3 dB, 6 dB, or 10 dB? And was it different for the pulses versus the pink noise? For the next set of tests, which was the minimum amount of dB change that you can hear, I'm going to play those tests back, and I've added in the dB level changes so you'll visually be able to see what's happening as you're hearing it and correlate the two, so you can determine which of the fruit or tool was a change of how many dB or no change at all. All right, so were you able to hear the 3 dB changes? And you are a normal person? Were you able to hear the 1 dB changes? And you are a super normal person? Or perhaps the 0.5 dB changes, which makes you a double super normal human? Also, did you find that the pulse test was not as definitive or harder to hear differences than the pink noise test? Well, the pulses is a little bit deceptive because they're spaced far apart and there's a lot of dead time between them. The average energy is not changing as much. If you do a 10 dB increase, the average energy is only increasing a fraction of that. So here's another test where I've clipped the pulses down and put them much closer together and see if that changes your perception of pulses. So what do I think? I think that 6 dB sounds twice as loud, 10 dB sounds 3 times as loud, and 3 dB sounds a little bit louder but not twice as loud. I think that I can hear, in fact I know that I can hear the 3 dB differences, I can hear the 1 dB differences every time, and the 0.5 dB most of the time. It's a little tricky with the pulses, and it depends really on what you're listening to the tests on, and that will vary greatly, and there's going to be a lot of different playback hardware for everyone listening to this, which will be really interesting information, and you might want to try listening on different things. Let's talk about dB increases as it relates to sound. If you take a signal and you add it to an identically timed version of itself, you just double it, you put two of them together, you're going to get a 6 dB increase in output level. And we can do that with pink noise. We can take a pink noise signal and we can overlay another pink noise signal right on top of it, or lay it on top of itself, and we will see the meters go up 6 dB. But if we take a pink noise signal and take a different pink noise signal that's not identical, and we overlay it, we're going to get 3 dB. Two disparate signals that don't add, two decorrelated signals, will sum. If they're equal in level when you start, they'll give you a 3 dB increase in the output level. But if they're identical and timed identical, they'll give you a 6 dB increase. This is one of the aspects of power alley. When you have a mono signal that's going to both sides of the PA, and that signal is sent identically to both, you get a 6 dB boost in the center. If you have one guitar to one side and another guitar to another, or totally decorrelated signals, you'll get a 3 dB boost. This is important and impacts us in many ways, and it's good to know. And we can do an electronic test of that with pink noise, adding decorrelated signals together and adding correlated signals together, and look at the difference in level output. All right, so let's see what happens when we sum together correlated signals and decorrelated signals. So I've got this pink noise file here, and we can fire that up. And we see that we've got about a minus 12 dB on the meter here. Now if I take this and duplicate it, fire that up, we can see we've got minus 6 dB on the meter. We gain 6 dB by laying the identical signal on top of each other. But what if these signals are the same level as they are now, and they are decorrelated, as in not doing the same thing at the same time? So we'll slide them off. Doesn't matter as long as it's longer than lowest frequencies you're dealing with, otherwise it'll just create a phasing issue. All right, so let's go ahead and fire that up. Reset the meter. And now we've got minus 9. Perfect. We gained 3 dB with decorrelated signals and 6 dB with correlated signals. So does this actually play out in the real world? I mean, we look at it electronically, we can recreate it. But can we recreate it in the real world? Again, I hate to take something for granted. I want to test and prove everything. So let's go ahead and do that. All right, so what I'm going to do is I've got these two little wedges here with the little ports lined up right on this microphone. So it's going to pick up just the low frequency energy coming from the two speakers, or whichever one's active. And then I'll unplug one of them, and we will look at the level, we'll listen to the level, and then I'll plug the other one in, and we'll see if that goes up 3 dB or 6 dB. Well, all right, so we'll check those results out and see what it comes up with. All right, so down below is the audio track we just listened to, and you can see where it's smaller getting bigger. and I'll right click on it and we'll look at the peak amplitude. And we can see here it's 22.1, and then we'll right click on the two speakers and we can see that it's 16.5. All right, to finish this video up, I've put together a whole bunch of different listening tests with various noise spectrums. Pink noise, blue noise, gray noise, brown noise, violet noise, orange noise. No, not orange noise. But a bunch of different noises, and they each have different frequency contents ranging from rolling off at 6 dB per octave in the high end to rolling off 6 dB per octave in the low end, and a tone and some other stuff. And there's a whole bunch of those, and I've listed what the levels are, and you can listen to those and let me know what you think, and let's get some groupthink information together in the comments section and see where it takes us. right, so you made it through the endurance run of audio noise, and now it's time to get up and stretch your legs. Let's see what Mr. Bones and DB, also known as Death Biter, would like to do. Who wants to go for a walk? Woo woo! Who wants to go for a walk? Who wants to go for a walk? Woo woo! Woo woo! Who wants to go for a walk? Who wants to go for a walk? Who wants to go for a walk? Anybody want to go for a walk? What? Is that a maybe? Anybody want to go for a walk?